Shri Gurubhyo Namaha children. Welcome you for our online teaching academy Ekalaiva. Today we are going to continue with 12th standard state board physics chapter number 4 electromagnetic induction and alternating current. We are going to discuss RLC circuit. Now let us consider a circuit containing a resistor whose resistance is considered to be R, an inductor of inductance L, and a capacitor of capacitance C. All are connected in series across an alternating voltage source. So the voltage applied alternating voltage is given as V is equal to Vm sin omega t, where Vm represents the maximum voltage, omega represents the angular frequency, and t represents the time, and V represents the instantaneous voltage. Now I allow current I to pass through this circuit. Okay. So when I allow current to pass through this, there will be a voltage developed across R, L and C. Okay. So the voltage developed across R is given as VR, which is in phase with the current. And the voltage developed across L is given as VL. Now, where the voltage here leads current by a phase angle of pi by 2. And the voltage across the capacitor is given as VC. And here the voltage lags current by pi by 2. Now, all these concepts we are already familiar with, right? Okay. Now, we are going to go in detail what will be the value of, to find out what will be the value of current and also the value of phi, that is tan phi, which we are going to see at the end of this topic. Okay, so let us move on to the phasor diagram of this circuit. So this is the phasor diagram for a series RLC circuit. Okay. Now here, look at this diagram children. Here we have drawn the phasor diagram with current as the reference phasor. Now this is the current phasor, which is represented in green line with the arrow head moving towards here this direction. This represents current phasor. Now this is considered to be the reference phasor. Okay, and this is represented as OI. Okay, OI vector. This is the current vector, or you call it as reference phasor. Reference phasor, which is the current. Okay, right. Next comes VR. Okay, so VR is represented as OA. So OA vector is VR, the voltage developed across the resistor. Okay, ma? Right. Next comes is the OB vector, which is nothing but VL. Now this OB vector will give the value of voltage developed across the inductor. Okay. And this is the third voltage phasor, which is OC vector, which is equal to VC. Here VC represents the voltage that is developed across the capacitor. Okay, ma? Now we know the value of this VR, VL, VC, etc. Now VR is nothing but, now VR is I into the voltage that is developed across the resistor is equal to the current into the resistor. Okay, Im into the value of the resistance. Okay, so VR is equal to Im into R. Similarly, here OB represents the voltage developed across the inductor, which is given as VL, which is equal to Im into XL. Okay, and XL represents the inductive reactance, right? Similarly, VC is nothing but Im into XC. Okay, XC represents the capacitive reactance. Now, all these formulas we have already discussed in our previous videos, right? Okay. Now, the length of these phasors, I said OI represents, this represents Im, which gives the maximum value of current, and OA represents Im into R, OB is Im into XL, and OC is equal to Im into XC. Now, to determine whether the circuit is effectively an inductive circuit or a capacitive circuit, now that depends on the value of the voltage that is developed across VL and VC. Now look at this phasor diagram, children. Now here we already know that in a resistive circuit, the current and voltage are in phase. Okay, the current and voltage are in phase, so both the phasors are in the same direction. Now this is the voltage phasor, this is the current phasor, so they travel in the same direction, which states that the current and the voltage are in phase with respect to a resistive circuit. Okay, now here this is the voltage phasor due to an inductor. Now we all know that in an inductive circuit, the voltage leads current by a phase angle of pi by 2. So here with respect to this, I take a phase angle of pi by 2, which is 90 degrees. So I draw this voltage phasor with a phase angle of 90 degrees. So because voltage is leading, so this phasor has to be in this side. So this is the voltage phasor with respect to an inductive circuit, 90-degree phase angle. And in a capacitive circuit, we know that the voltage lags current. So look at the phasor here. Now again, it lags by a phase angle of pi by 2 once again. So it is lagging behind a phase current by a phase angle of pi by 2. So when I draw a capacitor, VC phasor, now here I will be drawing the capacitive phasor. Here this is the value, this is the phasor, right? So what should be the value, whether it is inductive or whether it is capacitive, that depends on the voltage between VL and VC. Okay, now here we are going to consider, let us take VL is greater than VC. Okay, let us assume that VL is greater than VC. So what will be the net voltage drop? The net voltage drop across this LC combination, okay, across this LC combination will be the difference between VL minus VC, and this VL minus VC is represented by a phasor OD. Now look at this phasor diagram once again, children. Now when we draw the phasor diagram for the voltage phasor for an inductive circuit, look at the length of the phasor when compared to this length. This is the voltage phasor for a capacitive circuit. Now compared to this, this is a lengthy, which means here we assume that VL is greater than VC, which means VL phasor is greater than VC. So what will be the resultant voltage? The net voltage will be the difference between these voltage phasors, which is given as VL minus VC, because VL is greater than VC. And what will be the direction of this? The direction of this will be along the vector whose magnitude is greater. Among these two vectors, VL is having greater magnitude. So the resultant of this vector is also drawn in this direction, which is represented as OD. Hope you are understanding this concept very clearly, children. So what is this? This is the net voltage drop, net voltage drop across LC combination. Okay, and this is represented as OD vector. Okay, ma? Clear? Now I am going to, now what happened here is, now this is a voltage phasor, this is a voltage phasor, this is a voltage phasor. So there are three voltage phasors. Now what is that we have done here is, by finding out the voltage drop across L and C, we have reduced these three voltage vectors, three voltage phasors to two. So how will the diagram will be now? Now this is x-axis. This roughly I am drawing, children. This is y-axis. Now this is the voltage phasor and current phasor for a resistive circuit. Okay. Now this I have drawn the resultant. So the resultant is along, sorry, 1 minute. So the resultant is along this direction. So I will take this alone, children, which is represented as OD vector. Okay. Now what will be the resultant of these two vectors? The resultant of these two vectors will be along this direction. Now I am going to apply parallelogram law of vectors, which you have already done in your 11th standard, to find out the resultant of these vectors. So this is the resultant, which is represented as OE vector. Okay, so this OE vector will give the value of the resultant voltage V of VR, and this is nothing but VL minus VC, children. Am I right? So this OD vector represents the value of VL minus VC. So this OE vector will give the resultant value of VR vector and VL minus VC vector. Is it clear? So this resultant is along this direction. So I am going to find out the value of this by applying parallelogram law of vectors. So this diagram, we have taken it separately. Hope now you are able to understand this diagram. Now this is VL. Now children, listen here. If this is going to be VL minus VC, this value also will be equal to VL minus VC. So this triangle is taken. This is O, E, and let me name this point as A. So this triangle is drawn separately here. Hope you understand this triangle now. Now I am going to find out what is the resultant voltage V. Okay. Now V. Now this resultant voltage is due to VR and VL minus VC. Okay, and this is the length. So I'm going to find out the length as well as the angle by applying parallelogram law of vectors. Hope you are understanding the theory concept clearly. Now we'll go to the resultant part. So this is represented as, now this OE is nothing but VM. Okay, this gives the maximum value of the voltage, which is represented as VM. So I will write VM square equal to VR square plus VL minus VC the whole square. Look at this diagram again. OE vector is equal to VM. This VM is Pythagoras theorem. Now I will take the square of this, VR square plus VL minus VC the whole square. Okay, right. Now I know the value of VR. So what is the value of VR, children? VR is Im into R. Then VL is Im into XL. VC is Im into XC, right? I'm going to substitute these values in this equation. Okay, so I want the value of only VM. So what do? I take the square of it. So this will be VR square plus VL minus VC the whole square. Now substitute the value, ma. So root of VR becomes IMR the whole square plus VL is IM into XL minus IM into XC the whole square. Now here IM is common. When I take the IM from the square root, when it comes out as IM. Okay, so simply I will have inside R square plus XL minus XC the whole square, which is equal to VM. Okay, ma? Right? Now I bring this IM to the left hand side. So IM now will be VM by root of R square plus XL minus XC the whole square. Now I replace this R square plus XL minus XC square is equal to Z. Now this Z is nothing but you call it as impedance. So Z is equal to R square plus XL minus XC the whole square. So I replace this now. So the equation now becomes IM is equal to VM by Z. So this Z represents impedance of the circuit. Impedance, otherwise also called as resistance. Impedance of the circuit, which means now this impedance always in a circuit, what is the function of a resistor is to oppose the current, to oppose the circuit current. Now here also this value of Z, which is due to R square XL minus XC all square. So this will do the opposition work, okay, to the circuit current in the RLC circuit. Okay, is it clear? So this is the equation which is considered to be a very important equation. IM is equal to VM by Z. Okay, so this is about the resultant, where the resultant is Z equal to this. Z takes the value of root of R square plus XL minus XC the whole square. Okay, now let us look into the voltage and impedance triangle. Now we have found out the resultant using parallelogram. We have found out the value of IM. Also, we need to find out the phase angle. That is why we have drawn this triangle with the value of impedances. Now here this is phase angle. Phi is the phase angle between this Z and R. Okay, impedance and R. I need to find the value of phi. So let me take tan phi. Okay, so what will be tan phi here? So tan phi will be what are the values? Tan theta is opposite side by adjacent side. So here also opposite side by adjacent side. So let me write VL minus VC by VR. This is also equal to XL minus XC by R. So this is a very important formula which gives the value of the phase angle between R and Z. Okay, and we are going to discuss special cases based on this. Okay, so we have found out the value for the maximum current, which is given as IM is equal to VM by Z, and we have also found out the value of the phase angle, which is given as tan phi, or phi I can write as phi is equal to tan inverse of XL minus XC by R, or tan inverse of VL minus VC by R. Okay, so let us move on to the special cases here, where we are going to consider the first case. If XL is greater than XC, which means here XL represent the inductive reactance and here it is capacitive reactance. So if this is going to be greater than this, definitely the difference between this is always positive. Yes or no? Because this is going to be greater. When you substitute here, this will be greater. Then definitely XL minus XC is positive, and not only this, the phase angle which is phi, the phase angle phi is also positive, is also positive. So this is the first condition, right? Which means, what do you conclude from this? Okay, so here we talk about the applied voltage and current. Now this, in this case, the circuit will be highly inductive. So in an inductor circuit, we know that the applied voltage leads the current by a phase angle of pi. So here this, and this condition, we can say that the applied voltage leads current. Okay, leads current. What is a phase angle? By a phase angle of phi. Or I can also say that the current lags behind the voltage by a phase angle of phi. And we know the equation. So what is the voltage equation here? What is the current equation here? Now voltage equation is V is equal to Vm sin omega t, and current equation is I is equal to Im sin omega t minus phi. Now here this we have already done. Now instead of phi, we would have written pi by 2 in the case of an inductive circuit. So this is for the case XL greater than XC. Okay. Now the second special case is XL lesser than XC. So if XL is lesser than XC, now what will be the resultant? What will be the difference? Here you will have the difference XL minus XC to be negative. Okay, if this is going to be negative, what happens to the phase angle? The phase angle phi is also negative. Okay, so in this case, I can say that the current leads voltage by phi. Now here I can say, because here XL minus XC is negative, okay, and you have capacitive reactance to be greater than XL. In this case, the circuit will become purely capacitive, okay, and we all know the equation for voltage, Vm equal to sin omega t, and I is equal to Im sin omega t plus phi. So here the current leads, okay, the current leads voltage by a phase angle, oh I forgot to write here, by a phase angle of pi, which is equal to pi by 2 here. Clear? So this is with respect to XL lesser than XC. Third case is if XL is equal to XC. So when capacitive reactance and inductive reactance, when they are equal. So in this case, the value of phi is also equal to 0. So in this case, since there is no reactance, see, look at this equation once again. Here, if this is going to be this, then this will be 0. The entire term will be 0, right? So in that case, you will have R square, Z equal to R square, and the circuit is considered to be purely resistive. Okay, in that case, I have the voltage equation to be V is equal to Vm sin omega t, and current equation to be I is equal to Im sin omega t. Okay, so these are the very important special cases that has to be discussed in a RLC circuit. Okay, ma, hope the concept is clear for you. Go through the information that is given in the textbook related to this topic. See you in the next video, children. To subscribe for our YouTube channel, please press the subscribe button, and you will be receiving our latest updates. Thank you, children.